Our entire lesson today is devoted to this triangle. It's a special right triangle because the two acute angles are congruent. They're both 45 degrees. And if you remember a little theorem from back in the day, if those two angles are both congruent, then the sides opposite them are also congruent. Tick, tick. And so you might call this an isosceles right triangle. And we're here today to study the lengths of the sides of a 45, 45, 90 triangle. That's what they call this type of triangle. Now, if you remember on your practice quiz, we actually studied some of this type of triangle. We studied some isosceles right triangles, and back then we used the Pythagorean theorem to figure out how long those hypotenuses would be. And we found sort of a cool property that the hypotenuse was always the length of that leg times the square root of 2. And that's exactly the relationship we'll be talking about today. If I told you that this leg of the triangle was 9 units long, obviously this leg is also 9 units. But we could also, without using the Pythagorean theorem, we can say that the hypotenuse is 9 times the square root of 2 units long. That relationship works for every 45, 45, 90 triangle. There's even a theorem that goes with it. It says in a 45, 45, 90 triangle, the hypotenuse is the square root of 2 times as long as each leg. And that idea you'll want to memorize because it's going to come up again in Algebra 2 and pre-calculus and calculus. Anytime you talk about trigonometry, you're going to be talking about 45, 45, 90 triangles. And what we should be able to do is if we see a 45, 45, 90 triangle that has 2 legs of 17, we should just automatically be able to fill in the hypotenuse as 17 times the square root of 2. It's not going to trick you if they twist around that triangle, right? So I see the 45 and the 45, which means if that's a 61, this must be a 61. And right down here is the hypotenuse. And so the hypotenuse will be 61 times the square root of 2. And maybe that seems pretty simple to you. The only thing that complicates it a little more is when I start putting weird numbers on the legs. But it's not too bad because let's look at this first example. On a 45, 45, 90, I always know that those 2 legs are congruent. So if this guy's going to be 6 square root of 2, this is going to be 6 square root of 2. No problem. Now that's a little weird because there's already a square root of 2 on there. But here's what we need to remember is that whatever is on the leg, whatever the length of the leg is, all we have to do is take that times the square root of 2 and we'll know the hypotenuse. So even if it's something funky, we will just take whatever the length of the leg is times the square root of 2. And so we're going to want to simplify that. What is 6 times the square root of 2 times the square root of 2? Well, that'd be 6 times the square root of 4. And the square root of 4 is 2. And so it's looking like the hypotenuse is 12 on this one. So that might have felt a little strange, but really all we were doing was taking the leg times the square root of 2. To go from the leg to the hypotenuse, all you do is multiply by the square root of 2. Let's do another one. Here's my right angle, here's my hypotenuse, so I know that these 2 legs are congruent. If that's the square root of 6, then this is the square root of 6. And how do I figure out the hypotenuse? I simply take the length of the leg times the square root of 2. And so it's kind of a strange number, square root of 6. We're going to multiply that by the square root of 2. And that equals the square root of 12. Now I do want you to write those answers in simplest radical form. I know 12 is 4 times 3. And I can do that square root of 4, but the square root of 3 is kind of funky. So I'm going to say that that's 2. And leave that 3 under the square root. On this one, the hypotenuse has a length of 2 times the square root of 3. And yes, those 3 numbers would still work in the Pythagorean theorem, but we really don't have a need to use the Pythagorean theorem when we're talking about this special kind of triangle. Let's do one more example of 45, 45, 90. If we've got 7 divided by the square root of 2 on this side, then we've got 7 divided by the square root of 2 on this side. And the hypotenuse, even though I already see a square root of 2 there, which is kind of weird, I know the hypotenuse is always the length of the leg times the square root of 2. Every time. Every time. So that hypotenuse will just be the length of the leg times the square root of 2. And if you want to think of that as the square root of 2 over 1, you sure could. If we multiply straight across, because it's fractions, we have 7 square root of 2, and on the bottom, square root of 2 times 1. And the square root of 2 divided by the square root of 2 is just 1, so we would have a hypotenuse of 7. Now you'll notice for each of those examples, they gave me the length of the leg. And if I know the length of the leg, all I must do is multiply by the square root of 2. What do you think would happen if they gave me the hypotenuse? Well, that's what these examples are for. So if I know what the hypotenuse is, just think of this as doing the opposite, right? If I knew this, I would multiply by the square root of 2. How do you go backwards? What's the opposite of multiplying by the square root of 2? Dividing by the square root of 2. And this first one might seem kind of obvious, but the idea is if we know the hypotenuse, we will just divide by the square root of 2 to get this shorter length, right? When you divide by a number like 1.4 or whatever, you're going to get a smaller length, and that will stand for the length of that leg. Well, the length of the hypotenuse divided by a square root of 2 is just 8. And that checks out to what we were noticing with that pattern earlier, that if we had an 8 here and an 8 here, we would have an 8 square root of 2 on the hypotenuse. The next one's a little more challenging because there isn't that square root of 2 on the hypotenuse. It's just a straight up 10. So if I wanted to find the length of the legs, I would just take 10 and I would divide by the square root of 2 because I'm looking for a smaller number, right? So I would divide, and 10 divided by the square root of 2 is the length of that leg. And if I weren't so picky, I would just let you circle that and call it a day. But math teachers have this thing where they don't like to see square roots on the bottom. I like to joke that we don't think roots belong underground. So a math teacher does not want to see your final answer having that square root under there. But we do want this number. 10 divided by the square root of 2 is the correct number. What we're going to do is we're just going to fix this up. And we're going to fix it up by multiplying by 1. Maybe you're thinking back then, multiplying by 1, that doesn't change anything, which is a good thing because I don't want to change the answer. But I'm going to be creative when I multiply by 1. I'm not going to just multiply by 1. I'm going to multiply by the square root of 2 over the square root of 2. And we know that that's just 1. Let me show you what happens when you multiply by square root of 2 over square root of 2. On the top, we get 10 times the square root of 2. On the bottom, we get the square root of 2 times the square root of 2, which is the square root of 4. And I can do the square root of 4. That's why this little move works so well, because do you see how there's no root in the denominator anymore? That was the goal. I'm going to take this one step further because I can reduce. You guys, what do you think? Can I reduce the 10 over 2? Or can I reduce the square root of 2 over 2? And the rule is that we'd be able to reduce the 10 over 2 because there's no roots involved there. So 10 over 2 reduces to 5 over 1. So this would just be a 5 on top with its square root of 2. We could put over 1, but I don't wanna. So what we just found out is that the length of these legs are 5 times the square root of 2. 5 times the square root of 2. And we could double check that. If we took the length of the leg times the square root of 2, we should get 10. I think we should practice another one. If our hypotenuse is 16, how do we find the leg? You might want to remember this like this. Is the leg going to be shorter or longer than 16? Shorter. The hypotenuse is always the longest. And how do you make a number smaller? By dividing. That's So we're going to divide by the number of the day is the square root of 2. Now I can't just leave 16 divided by the square root of 2 as my answer. I'll give you a partial credit for that, but we don't like to see those roots on the bottom. So let's fix that up. Do you remember that fancy move I do? I multiply by the square root of 2 over the square root of 2, that creative looking 1. This technique actually has a fancy name. It's called rationalizing the denominator. On the top, I'm getting 16 square root of 2. On the bottom, I'm getting square root of 4. And again, the square root of 4 is just 2. And I can reduce that 16 over 2 to 8. And so I get 8 square root of 2 for those two legs. And I'm sure you pattern people are starting to see maybe a shortcut, but it's definitely still important that we understand what that rule is, that if we know the hypotenuse, how do we get that shorter leg? We always divide by the square root of 2. So no matter what number I throw here, it could be a whole number, it could be some funky root number, you know that whatever I have on the hypotenuse, I will divide by the square root of 2. Let's try this one. 7 divided by the square root of 2. You'll get partial credit for writing that. That's the correct number, but it's not in good form. Makes math teachers cringe. So we are going to rationalize the denominator. That just means we're going to make the denominator a rational number. Square root of 2 is irrational. And this time the 7 over 2 doesn't reduce, so I think most people would just write 7 square root of 2 over 2. I suppose some people might write 3.5 times the square root of 2. And this other leg would have that same length, because all 45, 45, 90 triangles are isosceles. You know, there's lots of ways to think about this, but I've had the most success teaching this method. That if you know this bigger number, to make it smaller, you'll divide by the square root of 2. And if you know this shorter leg, to make it bigger, you'll multiply by the square root of 2. That idea works for most people. If you're having trouble, just know that I can explain it to you in another way. If I were trying to find this leg, you could say that the hypotenuse is equal to the square root of 2 times the leg, and you could solve for x algebra-wise. But even that technique requires that you memorize that square root of 2 relationship. Another technique is using proportions. You guys are so good at this by now. If you can just know that there's this basic building block of all 45, 45, 90 triangles that have sides of 1, 1, square root of 2. Well, every 45, 45, 90 triangle is similar to a bigger one or even a smaller one. So we could solve for the side of a leg by saying, okay, well, the 1 is to the x as the square root of 2 is to the 6. And we could cross multiply to solve that. But again, it does require you to memorize that basic little triangle that has that relationship of 1, 1, and square root of 2. So no matter what we do, you got to know the special number of the day is the square root of 2. The method I'll be using most often is I either multiply by the square root of 2 to get a bigger number, or I divide by the square root of 2 to get a smaller number.